All right, everyone. We're team number 6. I.S.D stands for Innovative Sustainable Design. My name is Borhan Moradi. This is Richard Turkson and my friend Jarrett Habu. Here is the table of contents, all the topics that we're going to go over today. Problem statement, project description, compost, treatment methods, design items, site visit, Gantt chart, and advisors.
So for a problem statement, there's a scarcity of water. We're living in a desert. We don't get that much rain. So it's hard to get, good water. And so we're going to look into tapping into non-traditional sources, such as the shallow groundwater. And then the problem with that, though, is there's, residents, they have their houses, their foundations possibly can get weakened by it. They could hear noises if the water is moving too fast. And then, with weakened foundations, it decreases their property values because it's, harder to sell if they want to sell. And then also in the image, having your house next to, a bare piece of property also doesn't help your, what do you call it? The property value. So for a project description, on that piece of property, we're going to design a compost facility, have a permeable foundation, which will allow water to seep in and pool in a storage area, and hopefully help clean out some of the particles, the bigger particles that would be in the water. By doing that, we'll capture the shallow groundwater, and then in turn, we'll design a pump system and network to help capture the water that we've pooled and in turn use it in our facility, which will be, and then sell the compost. And then, so this is our piece of property. You want to just kind of highlight the little area with the mouse? Or it's on Southland Boulevard and East Reno Avenue. And so compost, for it to work, has to have proper aeration. The bacteria needs air to do its work. It needs adequate drainage. The bacteria will obviously not work too well if it's sitting in a pool of water because it takes out the air, and the bacteria are going to die. But it does need sufficient moisture because the bacteria do need, a little bit of water to survive. There's the carbon to nitrogen ratio. The green is nitrogen in generally wet products such as grass or food scraps, and then the brown is high in nitrogen and high in carbon and generally dry. This basically hay or leaves. And then composting works best in a few seasons, autumn and spring, because it's fairly warm and damp. But winter, obviously slows down the bacteria, so it takes longer to compost. And summer, you have the possibility of drying out the compost because of the direct sunlight on it. And then, obviously with compost, there is the possibility of smell, but it can be controlled by having a proper carbon to nitrogen ratio. But if there's too much carbon, it slows down the breakdown of the materials. But if there's too much nitrogen, it can escape into the air, and that's what's causing your odor. And then if it's also too wet, then that also causes odor.
So based on research, we've actually thought about using these 3 kinds of water treatment methods. We have the chlorination, we have the filtration by activated carbons, and then we have ozonation. Now, chlorination, basically deals with, adding chlorine in the water, to disinfect the water. get all the microorganisms and the bacteria out. Next, we're going to filter the water by using activated carbon. Pretty much, the activated carbon has a larger surface area, so what's going to do is it pre-sieves and disinfects the water before it goes through all the three necessary stages for for purification. And then the ozonation too is pretty much infusing an ozone, and an ozone is a gas where this ozone gas is going to be subjected to high electricity voltages, and that's also another treatment method that, if needed, would be considered for our treatment purposes. The next that we're going to talk about is the design items, and pretty much we're going to be looking into the composting facility, and that's actually going to encompass majority of our design. We're also going to look into permeable foundations, since we're actually dealing with shallow groundwater. So our plan is to look into the soil and go as deep as possible to be able to get the water out of the soil. And what we do is we're going to build a permeable foundation that will drain the water from the soil to be used for our purposes. And then we're going to design the pumps, which will literally transfer our water to the treatment plant for treatment, as well as using it for compost. The next is we're going to design our pipe system where we have to reroute all the water system through the ground to the treatment, the facility for treatment. Economic feature and salability. So we trying to target the traditional and then the non-traditional market, and mostly is about the farmers, because our future goal is to get fertilizer. And what we're going to do is we want to be able to sell the fertilizer to the farmers. And lands that are not highly nutritious to cultivate crops, the farmers can use these fertilizers to to boost that nutritional value for the soil, for the crops. Considering that there's a high demand of food that needs to be supplied to human beings. Human beings have to depend on food to survive. So farmers come in there to provide food for us. So we have to provide fertilizers for them as well. And the type of fertilizers that it's actually in high demand, it's called the nitrogen fertilizers. Now the soil amendments is where, like I said before, the soil is not rich, and so they're going to use what we get out of our compost as a way to neutralize the soil. Now we're also going to target the turf market. The turf market it's pretty much a non-traditional market, and those guys who go the grasses, so they can use our compost for golf courses, for athletic fields, and home lawns as well. Site visits. We have 3 samples that are in testing, and what we're going to do is we want to get the moisture content, as well as we're going to run more tests to classify what type of soil we need, and if we know the type of soil, then what's going to happen is we're going to design so many parameters to get us to be feasible with the soil classification. Now we're also going to look into the mechanical properties of the soil. Once we've classified the soil, then we're going to have to look into the strength of the soil. That's about it. Maybe the permeability of the soil too as well. We're also going to target flow rate of the water. Pretty much we want to see how fast we can get water to fill in the well. And we're also going to find out the type of contaminants in the water so that we can design a specific water treatment for it, either to be safe water or to be drinking water. So.
And here's our Gantt chart. 31 tasks that we have came out with. Some of them are progressing. We're like 70% done with some of them. Some are 100% done. We're doing some research, advisors, meeting with advisors, designs, and so forth. Some of them are linked to each other. As we can see, once we find out the type of a soil, we're going to start working on the foundation, so they have to be linked to each other. Once we find out what the flow rate is, we can start working on the pump design and so forth. And as you can see, most of them are going to be done by middle of April. So we're trying to be ahead of time, and that way we can start working on our model. These are our advisors that we got. Dr. Kuseiko, Jeffrey Jensen, basically all the information for those guys. Dr. Thomas Piero and Dr. Ahmed are helping us on the project. And that should do it. Any questions? Any comments?
When you guys say you guys are going to test the contamination in the water, are you guys physically going to go in there and get a sample and test it you guys yourself? Or how are you guys going to test to see what's exactly in that water so you guys can treat it? How are you guys going to do that?
Well, we're trying to get into the land and basically drill a hole in the land and take some water out, take it to the lab and see what type of contaminants are in the water. So we actually going to go to the land and take water.
Any other questions?
I have some.
Sure.
Do you have any idea how much water we can get using the proposed method?
Well, we can't answer that till we drill some holes into the field and find out how much water we have, in the groundwater table. Once we find out how much water we have, how much potential water we have available there, then we're trying to get like about 90% of that water being pumped to the facility. So in terms of the volume, we don't have the information yet.
Do you have an idea how deep you have to go?
Well, we believe that we need to go around 12 to 20 feet down to get into water by considering all the works that SNWA have done around that area. They suggested us that, in that area, the average depth that we need to go in order to get to water is around 12 to 20 feet. It all depends, again.
And how was this site selected on the grounds of what? The location where you are planning to do?
Okay. Well, this actually was an EPA project. This was actually in a field that we chose for a competition for EPA. And this was offered to us by Jeffrey Jensen, who was coordinating the project. And he said that there is a groundwater table in that field, and that can be used for different purposes. So,
I have a question. You guys said you're going to test the contaminant in the water.
right.
Are you guys going to test the soil? And if so, how are you guys going to do it?
Well, we already have started testing the soil. We were in the field last Friday. We took 3 samples of the soil, as Richard mentioned in the slides. We're gonna classify the type of a soil. We're also gonna do some stress on the soil and particles to see how much pressure it can take, so that we start designing our foundation on it. We already have done moisture content as well as permeability of the soil. So we need to work on the how much stress it can actually take. So strength of the soil and triaxial tests and things like that.